Dear students, welcome to today's lesson. In this lesson, we are going to look about the general theory of relativity. Now, the general theory of relativity is an extension of the special theory of relativity. And the general theory of relativity, often called GR for short, was created in order to understand why gravity exists or what is gravity. We have all heard that Newton identified that gravity as one of the fundamental forces in nature, and even though he identified gravity, he couldn't exactly say how gravity occurs or why gravity is there or what is the reason behind gravity. So Albert Einstein, through his theory of general theory of relativity, aimed at finding a solution to the question what exactly is gravity and why does gravity exist in our world. So it helped us, the general theory of relativity, in other words, to identify what gravity is and why gravity exists. And the general theory of relativity has a lot of predictions which are very profound, and those predictions have been identified and by Albert Einstein, and they are proved with a lot of experiments, right? So before general theory of relativity existed, Einstein first came up with the special theory of relativity. And in special theory of relativity, he identified two moving frames of references and considered that the relative velocity between those two frames to be constant or at uniform velocity they were moving relative to each other, and applied his theory of relativity and arrived at conclusions. And this stream of thought is called as the special theory of relativity. And later on, Albert Einstein extended his special theory of relativity to reach the general theory of relativity, wherein the relative motion can also be non-uniform. One of the major theories or one of the major principles in general theory of relativity is called the equivalence principle. And the equivalence principle, it essentially says that there is no experiment that can be done in a small confined space or a lab that can detect the difference between a uniform gravitational field and a uniform acceleration. So, for example, as we can see in this image, imagine you are conducting an experiment inside an elevator. If the elevator is standing still on Earth, it is still being attracted by the gravity of Earth, which is around 9.8 meter per second squared. And if you are conducting an experiment, any experiment for that matter, imagine you are conducting the same experiment inside the same elevator, which is now moving upward at 9.8 meter per second square, which is exactly the opposite of what the gravity is, right? So these two experiments will produce the same result essentially. So that's what the equivalent principle says. That is, there is no experiment that can be done in a small confined space. Why in small confined spaces? Because if you have a large space, there can be indicators of the movement of the place, right? If there is a window to that elevator, you can see that the elevator is moving or not, right? So in order to avoid that, we are saying that it is a small confined space that can detect the difference between a uniform gravitational field and an equivalent uniform acceleration. So either if it's in a gravitational field or if it's being accelerated with the same amount of force, it would look identical. That's what the equivalence principle states. Now let us look into a little bit of history about the general theory of relativity, right? So it was developed between 1907 and 1915 by none other than Albert Einstein. And the beginnings of general theory of relativity started in 1907 with a thought experiment of his, uh, which he calls one of the happiest thoughts of his life, which is essentially if a person is jumping from the roof of his house, when he is in the air, he wouldn't feel any force, right? For him, the person who is jumping off the roof, as he's in the air, for him gravity does not exist. So it is essentially as same as he's floating in air. So if we look back into some of the experiments that we conduct for space travelers or astronauts, they go in an airplane to the atmosphere, and then the airplane is brought down without using the engine. So essentially they can feel the environment which is sort of similar to that of a vacuum. So it is almost as if gravity doesn't exist while they are in free fall. So that's what Albert Einstein thought about, and the general theory of relativity as was a result of that thought experiment. So he published his first paper applying special theory of relativity to accelerating frame of references in 1907. Then in 1911, he published a paper that predicted gravitational lensing, which we will look into a little bit further in this lesson. And in 1912, he essentially formulated a theory of space-time, which is purely geometry. Then in 1915, Albert Einstein developed one of the famous equations that we have come across in the field of physics so far, which is called the field equations. That was done in 1915, and the general theory of relativity was published in 1916. So this is somewhat the history of the general theory of relativity. And now let us look into some of the characteristics of a general theory of relativity. First of all, the general theory of relativity essentially supersedes Newton's theory. So Newton has identified what gravity is. He has said that gravity is a force of attraction that happens between every body which has mass and so on and so forth. But why gravity exists, or gravity was a force according to Newton, and why gravity exists was not answered. And many scientists were looking into answers to find the solution of the question why gravity exists. And Einstein sort of superseded that and said gravity is not exactly a force, but it is the warping of space-time. So space-time is a concept that includes both the space that we exist in and the time that we exist in. So space-time is a construct which includes both space and time. And Einstein said that gravity is the curvature or the warp in space-time, and what warps the space-time is the mass. So mass essentially warps space-time, and bodies move through this warped space-time, and that's what we see as gravity. That's what Einstein suggested through his general theory of relativity. And so that's what it said here. Essentially, massive bodies warp and curve their local space-time. So we'll see a diagram to explain the same thing. So imagine this sheet is space-time, and if you have a massive star here or a mass that is here, that mass of the star will warp the space-time just like a curvature. If imagine you have a trampoline or an elastic sheet that is stretched out, and if you are putting a massive ball, a bowling ball for example, on the middle of it, we'll see that there is a curvature, right? So similar to that, the space-time will be curved or warped by high mass objects like stars. And just imagine that the curvature of space-time is not in two-dimensional, but the curvature is in all directions. So it's not just in this particular direction, the curvature can be in this direction, this direction. So in all the possible directions, there is this curvature. So the curvature is three-dimensional. As the mass increases, the curvature also increases. For example, imagine this is Earth, and compared to a star, the Earth is a very small object. So the curvature of space-time due to Earth would be only this much. And a low-mass star could curve the space-time this much, and a high-mass neutron star would create a very large curvature in the space-time. So this is how the theory of general relativity put forward the concept of gravity, right? And there are many predictions of general theory of relativity. Einstein predicted this way back in the early 20th century, and all of these theories were confirmed through experiments and observations. So some of the major predictions of general theory of relativity are: one, gravitational lensing; there are black holes, gravitational redshift, and gravity waves. So these are four of the major predictions. There are also a lot of other predictions as well, but these are four of the major predictions that happened as a result of the general theory of relativity. And in the next lesson, we'll look into these four phenomena and see how they are predicted and how they were observed and what are the implications of the same. So see you in next lesson. Thank you.